All right, so rain aside, thank you all for trekking through what is apparently a severe flood warning. Hope we don't get swept away. Before we get started, or I guess to start tonight, basically this final week is just going to be a series of special topics, moving off of machine learning from last week. We'll do some text processing tonight. We're going to do some web scraping and API calls tomorrow, and then Thursday, again, people want a special topic, please email me. Otherwise, we're just going to do, I guess, in-class demos, and apparently there will be pizza and things.
Wait, really?
Hooray, come on Thursday. Okay, so before we get started, I just want to address a few questions that creeped up over the weekend. Apologies for my delayed responses over the weekend. I was outside, which was lovely. So the first thing is that for those of you who have upgraded your macOS to Sierra, you might be running into an issue where Jupyter Notebooks isn't launching. This actually has a really, really easy fix, but I just wanted to walk through it in class. So for those of you who are using Sierra, how many of you are actually using Sierra right now? 2 people. Is Jupyter Notebooks launching for you guys? Nope? Okay.
Yeah, it's launching for me for some reason.
You're running Sierra? Oh, strange. Okay.
I am too. Didn't realize.
Well, then maybe if it's just...
Yeah.
Well, okay, we'll do this super fast. All you have to do is open up a terminal. Once you have a terminal open, all you have to call is this command right here. So that's going to be Jupyter Notebook generate. Is that generate dash config? You hit that. I'm not going to run it because I did it earlier. Then we are going to I'm just going to copy and paste this command right here to open up our configurations file. You should get text edit, got a lovely little configuration files like this. We are going to search for this tab right here that says c.notebookapp.browser. Just put, right now it should be commented out for you guys. It should look like this, and then just empty brackets. Just put in your preferred browser into those quotation marks and get rid of that comment. So for me, that's going to be Chrome. If you're running Safari or Firefox, put in whatever works. So be it Chrome, Safari, Firefox. Close that. Save and close. Close the terminal, reopen. Run Jupyter Notebook or run Anaconda Navigator, and hopefully that should stop. It should actually load up to your default browser now. If it doesn't, we will debug after class, but that's what fixed it for me. Number 2, I just want to go over it again real fast, because a few people emailed me over the weekend to say that RPy2 wasn't installed, so they couldn't do some of the R demos. So this goes back to just the PowerPoints that we sent out earlier last week. To get all the R demos running, you're going to need to just follow the same set of steps that we talked about last week. You're going to need to open a terminal. You're going to need to run this conda install -c R and R essentials to install an R compatible version with Jupyter Notebooks. And then to install RPy2, you're just going to then, after that finishes installing, just do pip install upgrade RPy2. And then those built-in R examples that we did last week should run for you guys. So I just wanted to go over that real fast. Tentatively, because we've already run into issues with this slide, so I'm excited. Today, we will be working with the Natural Language Toolkit pack. Okay, Integrity. Yes, please record that. We're going to be working with the Natural Language Toolkit. We're going to be working with PyEnchant, and we're going to be working briefly. Oh, buddy, come back. We're going to be working briefly with PyCloud or WordCloud. So if you want to open a terminal or Anaconda prompt and just try running pip install upgrade NLTK, PyEnchant, and WordCloud. Fair warning, I've already apparently run into Windows installing PyEnchant for Windows. You're getting it too? Okay. If we're getting it for everybody, then we'll have to do a debugging. It's weird because it ran fine for me, but of course. All right. For those of you for it works, great. If not, I'll have either solution for you guys tomorrow, or we can work on it after tonight. Finally, the other thing I want to say is that, like I said, we're going to be going through text processing tonight. There is a ton to be said about text processing generally and a ton to be said about text processing for Python. There are really, really, really excellent tutorials, including basically this entire NLTK textbook is in this hyperlink right here. Can I just follow that? So you can get just an entire textbook that's all about natural language processing in Python for free. That's freely available to you guys. Also, Neil Karen is an amazing sociologist at UNC, and his entire bread and butter is doing really cool sociological text processing studies. His website has just like 24 Python-based examples of text processing for social data. I really, really recommend going through a lot of his stuff. They're just really fascinating examples applied to all different sorts of economic data, political data, really cool things. So I definitely recommend checking that out. Okay, off to an excellent start already. We'll come back to that at the end because that's more fun. Okay. Tonight, we're just going to go back to the notebook file. There's not going to be a demo file. So if you want to follow along passively, you can just download everything from the GitHub. If you want to follow along actively, hopefully you guys downloaded that zip file from the Dropbox that Megan sent around earlier. That's because as a demo today, we're going to be processing every single abstract that has ever been awarded money from the National Science Foundation in the past 10 years. And that's much too large to store on GitHub. So we'll get to that in a bit, but let's just start. Most basic thing in terms of text processing is that we're going to want to just quickly review strings again. So we're going to just breeze through this. Again, in terms of strings, anything closed by single or double quotation marks. Here we have an Abraham Lincoln quote about text, very exciting. Remember that strings have a bunch of different attributes that can be used to modify strings. So for example, we can do string substitution. We can count the number of A's in the string. We can also find where certain words appear in the string using the .index attribute. Importantly, you can force all the characters in a string to go to lowercase, which will be really important later on. We're actually doing corpus text processing. We can also replace elements in a string using the .replace attribute. And we can do things like splitting strings and joining strings back together. So we are able to split the string on every space, and we are able to join it back together after sorting it to get this entirely incoherent sentence. One of the big problems with the .replace command is that it is limited and that you can only replace one substring at a time. So what if you wanted to be able to access multiple parts of the string at once and replace multiple parts of the string at once, matching on some character? Well, of course, you guys probably already know from working with R that regular expressions is what you want to look at or what you want to work with. Have you guys worked with regular expressions in R before? Raise your hand if so. Some of you? Okay. Regular expressions is like a mini language within a language that allows you to just very quickly match text characters. So it's just basically a nice search syntax that allows you to say, okay, I'm going to find all of the punctuation in this sentence, or I'm going to find all the numeric characters in this sentence, or I'm going to find everything that starts with the letter A or ends with the letter T. It's its own mini language just because its syntax sort of counts as its own little mini syntactical language. Python, of course, has regular expressions, as does R. We're just going to import it by doing import RE for regular expressions. To get it to work, you need to define a pattern that you want to search for. So here, this complex looking pattern is actually pretty straightforward. We've broken it down. So /W means that at the beginning of the pattern we want to match, we want it to start with a white space. We're then looking for anything that follows, like that the first character should be an R that begins the word. Then we're looking basically for any combination of alphabetical characters. That's what these brackets mean right here. So basically anything that's in the alphabet between A and Z is what we're going to be searching for. And the asterisk means any infinite number of repeated alphabetic characters. So we're going to put that all together. really should split that actually. So you can see when we search for it up top, we got these words that start with R, which is great, which is exactly what we're looking for. We got rule and respect. But if we want to do something different, if we wanted to search for all string or any words in a sentence that ends with an S or a T, we could do something similar. We could look for the start of a word by, again, looking for the appearance of a white space. And then, again, any repeated number of times of alphabetic character. And then by putting in brackets, what we're saying is that we want to look for any appearance of an S or a T. And then, again, we want to find a word that ends with a white space. So by doing that, we can find all these words that end with S or T. So we got is, it, must, great, or its. If you've never seen regular expressions before, there is a link here that really goes over them in pretty extensive detail. There's lots of different search patterns you can use to find any sort of combination of text. We'll be using them a little bit, but I just wanted to give you guys a flavor of it. More importantly, later on down the line, what we're going to be using regular expressions for is basically to find all the instances of punctuation so that we can very quickly tokenize or split our text into individual words so that we can do some text processing on it later. And actually, to give you an example of finding all the punctuation, one thing that we can do is import the string library from Python, which actually nicely has encoded for all of us, or has stored in memory for all of us, every single possible punctuation mark. So let's print all that out. So you can see stored in string.punctuation are things like the exclamation mark and the quotation mark and the pound sign and the dollar sign, so on and so forth. And we can use the find all function from the regular expressions library to search for all the punctuation in our string. So this is what r.findAll is doing. You give it a pattern, a regular expressions pattern that you want to search for, and you give it a string that it's going to search through, and it's going to return all the instances of that pattern in the string. There's lots of different search patterns you can use. So for example, the /d regular expression means that you're going to be looking for all the instances of a numeric character. So we'll give it that /d pattern. And then in this string, my favorite numbers are 4, 24, and 48. We're just going to search for all the numeric characters, and that means we should only get the numbers out of that sentence. And indeed, that's what we get. So it works. In addition to findAll, the regular expressions library also has sub, which is substitution. So you can do multiple substitutions at once, which the replace attribute of base strings can't do. So again, right now what we're doing is we're going to look for every single instance of a punctuation in our original string, and we're going to replace it just with an empty space, where we're just going to basically delete it. If we want to replace it with a space, we could put a space in there, we put multiple spaces, but by having no spaces in here, that basically acts as deleting it from the string. And you can see now we got our quote back and just no punctuation whatsoever. So, okay. One other really basic thing to go over before we get started actually doing more formal text processing is just how to save basic text files. So earlier with pandas, we showed you how to save tab-separated files or comma-separated files. But let's say you just wanted to save the simplest text file. The syntax in Python is really, really straightforward. You're just going to be using this open command to specify that you want to open a new file for writing. So the syntax is just name the file that you want to open. So we're going to open this example lincoln.txt. And then you want to specify how you want to open it. So by specifying W means that we want to open it for writing. This is in contrast to putting R, where you'd be opening it for reading. So you wouldn't be able to modify the contents of the file. You'd just be able to read from the file. You could do single quotation marks A, which means writing to append. So you're not going to overwrite anything. You're just going to add new text to the bottom of the file. But when you open it with W, that means you're going to open the file and you're going to write the file. And if this file already exists, you're going to overwrite the file. So beware that if you want to just add to a pre-existing file, you want to open with A, you don't want to open with W, because W will overwrite.
So if you're going to do some manipulation to it, such as removing the punctuation, would you open it with W and then just rename it as something else, or what would you do?
We'll give you an example in just a second. It's a perfect question. So just to at least show you the writing portion, what we're doing right here is we're taking our Abraham Lincoln quote from before. I'm using the .write. So once we open a file, basically, it's going to return a new instance of a document, which I'm just going to call write file, but we could also equally just call this our new document, or Lincoln.txt, or just call it Lincoln or something. Don't zoom in. So if I do this, let's split this out just to show you what it looks like. So this is just a new instance of a document that we're writing to. So what I'm going to do is I'm going to take that instance and I'm going to write to it using the .write attribute, whatever our string is, so it's our string from above. I'm adding a new line character just for prettiness of our file. And when you say .close, that means you're closing the file for writing so that it actually writes to the file. So here's a case where if we wanted to do some modification to that file, we can now reopen it. So here I'm reopening it with A, meaning for append. This will allow me to modify the file without overwriting the contents of it. So for example, one thing that we could do is actually exactly what you just said before. We could take that same string, I'm going to pass it through the regular expressions.substitute or re.sub. I'm going to take the same quote, filter all of the punctuation out of it, and add it as a new line to that document. And so we'll reopen it again in Python, but I can also just show you what it looks like directly. So we'll go into that folder where we saved it. So now actually I've done it a few times, but here's our original quote, and here's what we just wrote right here. You can see where we saved it without the punctuation. So this just got saved into our new Lincoln example file. So here, before we were able to open it, we were able to modify it, and we were able to save it again. If you notice, the syntax changed a little bit between these two examples. Sorry. Took the wrong one. When we originally made the Lincoln file, notice how we did it in multiple lines. So I had a Lincoln open file and I had a Lincoln close file. Here the syntax has changed a little bit. I used the syntax with open file. This is sort of like a mini for loop for writing. Basically what it says is open up this file and save the instance as this variable, and then execute all the code beneath this line right here. And it'll execute all that code, and then it'll automatically close it for me. I don't have to do this Lincoln.close line. It'll automatically close that file for me. And just to show you an example of opening and reading a file, which is what we're going to have to be doing a lot when we're doing text processing, we're going to do the with open again. So I'm going to open up that file that I just showed you guys before. Notice that I'm specifying R, dash R to actually read it. And I'm going to open up this new instance as read file. And I'm going to use this new attribute we haven't used before. This new attribute is the .readlines, which is going to return all the lines in that text file basically in a for loop. It's going to return all the lines in that text file in a list that we can iterate across in a for loop. And I'm just going to print out all those lines. So we had 3 lines before, and we get 3 lines out. So just to make it explicitly clear, we opened it with open quotation marks R, it's passing the newly opened document as read file. I read from it with read lines, which returned all the lines as a list. I passed each line to the line variable in this for loop, and I just printed out the line. Is that clear to everybody? Okay. The reason why this is important, although it might seem sort of like a tried example, is because when we'll be doing lots of text processing examples, what we're essentially going to be doing is, for for example, in the NSF dataset that we're about to move towards, when you download the NSF dataset, you're actually going to get 10,000 text files. I mean, just like thousands and thousands of individual text files, each one containing the abstract for that grant that was awarded and all of its associated metadata. And all of them are going to be individually stored in individual text files. So if you wanted to be able to text process all of those things, you'd have to write a for loop that basically iteratively opened, read the lines from that file, did some text processing with it, and then closed that file. And a lot of the code that we're going to show below is actually going to do that and is going to make it prettier, and in the sense that there's going to be a lot of built-in code that will do all that reading for you, but I just kind of want to show you what's happening in the back end. Does that make sense to everybody? Okay. So for example's sake today, like I said, we're going to be going through this NSF data set. It's a lot of abstracts of data because the National Science Foundation is really cool. They basically have online all of the information for every grant they've ever awarded back since like 1963. That turns out to be an insane amount of data. We are just going to do the past 10 years, which is also an insane amount of data, but why not? The other thing I should point out is that for those of you who are interested in processing XML, which is a really common format for data to be stored, especially when you're pulling off the internet, we're not going to go through it in class, but I just want to make you all aware that if you go into the NSF folder in Module 4 on the GitHub, there is a notebook that's just all about parsing XML in Python, and it gives you a nice clean example of how to do it. So just in case you ever come across the XML format, there is a long tutorial for you. Just wanted to point that out. I'm going to skip over a lot of this code because a lot of it's just going to be showing you guys exactly what we did before and actually just sort of introducing you guys to the NSF dataset itself, just showing like how much money's been awarded over the past 10 years, by what directorates in the NSF, to what institutions. All that's interesting. If you guys want to see it, it's up on the GitHub if you want to get a nice overview of how the NSF's been dishing out money over the past 10 years and how the 2008 recession actually affected grant funding. But that's perhaps not as interesting. So there's just lots of plots that you guys can go through, but we'll skip over it. Let's actually get into the processing itself. So I'm going to break down many different steps of text processing, just sort of step by step, different problems you might encounter, and just different ways of handling it in Python. Once we sort of break it down step by step, then we'll go through an example at the end that sort of reassembles it into one long functional pipeline that was actually used to process all this NSF data into a tokenized format. So just to sort of give an overview, when we talk about when we talk about text processing, there's sort of a few main problems you're going to be running into. First of all, text is usually encoded in lots of different formats, and ideally you want everything in a UTF-8 format because that's sort of the universal format. Oftentimes when you're getting web data, or oftentimes when you're reading things from Word or other associated documents or PDFs, it's not in that format, and that's a huge pain in the butt because basically it'll turn into gibberish if you try to open it in any programming language and it's not in the right encoding format. So we're going to talk a little bit about how to solve that. We're going to talk a little bit about the tokenization problem, which means, okay, you've successfully been able to read an entire document, but you need to break down that document into its constituent sentences and its constituent words if you want to be able to do any meaningful analysis. So how do we do that? We're going to talk about parts of speech tagging, meaning that let's say you want to break down a sentence into its verbs and its nouns and its adjectives and its adverbs and all its constituent glue that holds sentences together, which is important if you're interested in the linguistics, but also really important if you want to do selective processing. So for example, if you want to do sentiment analysis, you want to understand how people are talking about something online, you might be very much more interested in the adjectives or the adverbs of a sentence. If you're more like some of the stuff that I've been doing, where you're really interested in understanding how people are talking about mental health symptoms online, you might be really interested in just pulling out all the nouns and things like that. So parts of speech tagging can also be really helpful when you are specifically trying to clean up words, which is the next thing we'll be talking about. We'll be talking about Stop words, so filtering out really common words that have very little informational content. Stemming words, so basically trying to remove the roots, or sorry, reducing words down to their roots. So taking off ing from verbs or taking off plurals from nouns, because then you're reducing just words down to their constituent elements, which means that you can stack them better when you're doing analysis at the end. We'll talk a little bit about spell checking, although it sounds like that's going to be an issue tonight because that package is not installing properly, and we will figure that out. And that should be the main pipeline, and then we'll throw it all together and we'll see what we get. So let's start going through it. So the first problem that you'll often run into when you're doing text processing is just the text encoding problem. File formats are numerous and complicated, especially if you're trying to read things like PDFs, especially if you're trying to read JSON or XML. It can be a real pain. So there's lots of libraries in Python that will try to do automatic, basically solving this encoding decoding problem, so detect what language a document is written in and convert it to a language that is easy to work with, or an underlying language that it's written in. So for example, just to show why, we have a document that's written in UTF-16, which is pretty simple, but not the UTF-8 that most packages are expecting. If we try opening that, you're going to run into a Unicode error, which just happens all the time. To get around this, we're going to import the codex library, and we're going to just have basically have it read things in as different encodings. In this case, it's really straightforward because in this case we know that the encoding is UTF-16. So you can see after reading in the codex library, I'm going to do codex.open. I'm going to specify the file that I want to open. I'm going to specify that I want to open it for reading. And I'm going to specify the desired encoding. So here I'm specifically telling it I want UTF-16, not UTF-8, which is its default. And then, great, I can actually read the contents of this. Codex has a lot of functions that can be used to sort of try to auto-detect what the likely encoding of the document is. This is obviously the simplest of examples because I knew exactly what the encoding was. We knew it was UTF-16 and not UTF-8. But if you need to, Codex has a lot of additional functions to help try to convert things back into UTF-8 so that you can open everything, read it all in, and do text processing. And just to give an example, we're going to read in the first abstract that was granted by the NSF in 2016. Yes, I can import OS. You are not wrong. And you can see we got a lovely abstract that talks a lot about mathematics. Okay. We're going to actually start moving into formal text processing now. So before, that's really just solving the problem of trying to get files to be read in. One of the main libraries in Python right now, probably the main library in Python right now for doing text processing is NLTK, or the Natural Language Toolkit. This package is really, really cool. I think it's originally out of Stanford. It's been worked on for like a decade now. Every major advance in CS and linguistics has been more or less operationalized in this package. It's huge and expansive and sprawling, and that's why they made the textbook available for free, because there's way too much ground to cover. We're just going to show you some basic examples, but if NLTK, or natural language processing, is sort of your bread and butter, I really recommend going through that textbook. So we're going to import it in the same way that we've been importing it before, but one thing I want to show you guys is that there are tons of corpora or just text libraries to be downloaded from NLTK, so things like WordNet or SystemNet or like Merriam-Webster. There's like tons of things you can download, and NLTK is great because they give you this lovely little GUI where you can actually just navigate through. You can do it from the command line as well, but it's nicer just to be able to pull this up real fast and basically just say, okay, let me just scroll through the things that I actually would want to look at. So we can go through all the, oh, it's actually downloading everything right now. Whoops, don't do that. You can see all of the different corpora that it has installed. It tells you what things are and are not already installed, and there's tons and tons of things that are already pre-installed here. So for example, if you wanted to be able to look through 100,000 books that have been digitized and stored, and you wanted to have a base corpus where you can look at the frequency of every single word in the English language and compare that against Twitter feeds, you can download all that from the NLTK library and use it as a base corpus with which to compare tokens to Twitter, Facebook, or any of these things. So just be aware that you have all of these tools here. Did you freeze on me? I bet you froze on me, because I just tried downloading several gigabytes worth of corpora. I'm just going to reload everything real fast. Okay. Great. Here, if you downloaded the data, all I'm doing here is just pointing NLTK to a path where I've already downloaded a few corpora so that NLTK can use it. That's all that's happening there. Okay, let's start with the first problem. As we go through this, everything we're going to be doing is working with this first abstract that I showed you here. And don't restart. What are you doing to me? One problem with these notebooks is that they're sequential, so if you restart it and try going through the middle, lots of things are going to have disappeared. Okay, we're going to be working with this abstract. So right now, it's this one long paragraph. The first thing we're going to need to do is we're going to be able to decompose all of this paragraph into sentences, because to do positions of speech tagging, you need to pass in each individual sentence, because the taggers can't learn things from words alone. It needs to learn things obeying actual sentence structure. So how are we going to break everything down into individual sentences? We're going to import from the NLTK library, from NLTK.tokenize, the aptly named sentTokenize or sentence tokenize function. And we're just going to pass in the entire paragraph. And you can see what we get out from it. We get this new variable sentences, which is a list of sentences that I'm just printing out here. So you can see, okay, so we get the first sentence of the abstract, this mathematics research project, blah, blah, blah. For example, the mathematical modeling, blah, 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 blah. So one line of code, we can immediately pull out each individual sentence. So that was just the sentTokenize function. The next thing we're going to want to do is break everything down from its individual sentences into its individual words. So remember from before I showed you regular expressions. When we want to break things down into their individual words, what we're going to want to do is we're going to want to remove certain things. So we're going to want to remove all the punctuation, because punctuation is no longer going to be helpful for us. We're going to want to be able to remove, in this case, I'm going to remove all of the, actually I'm going to keep all the digits. I'm basically just going to remove everything that isn't an alphanumeric character. So everything that's a number and everything that's alphabetical character will survive. Everything else is going to disappear. That's what this regular expression pattern is right now. And I'm going to import from NLTK the regular expression tokenizer, which is going to break down individual sentences into their respective words or their respective tokens, stripping away all the punctuation. So here's our first sentence, and you can see it's now broken down into its individual tokens. So we got rid of things like hyphens and semicolons and parentheses and everything. So we just got all the individual words out. So this is your clean, raw material here. And again, this was really, really straightforward. We just needed one function and one line of code. Once we have our individual words stored in sentences, so what we have right now after this line is a list of lists where each list contains each individual token. So I showed you the first list, which just is the first sentence, but we have 2 and we have 3. What we're going to do is pass each individual list from that list of lists through our position of speech tagger so that we can get out what are all the nouns, what are all the verbs, what are all the adjectives. To do that, we're going to import the POS tag function, position of speech tagger. And when we do that, we get this. We get a new list where every word is now stored in a tuple, where we get the original word, and we get its position of speech. These acronyms can be a little difficult to parse when you're first seeing them, but they're all explained in this table right here. So for example, in general, whenever you see a noun, it's going to start with an N, so that makes sense, right? Mathematics is a noun, analysis is a noun, geometry is a noun, areas is a plural noun, research is a noun. So that's good, it seems to be working. All the verbs intuitively start with V. So let's find a verb in here. Okay, concerns is a verb, great. Adjectives start with J, and adverbs start with J. And a lot of the sort of glue words like prepositions, conjunctives, determiners, all of those things start with other letters. If you want a full list of everything, it's all broken down here in this lovely little tutorial. And there's a huge list of all the parts of speech. And if you've ever taken a linguistics course, this will have been drilled into you mercilessly. What we're going to do then, so I just passed in the first sentence here, but we're going to do this for each individual sentence so that we can get the position of speech out for each individual token. So great. So the other thing that I did is I actually just stored everything into a NumPy array as well, so that we can iterate over it a little bit easier. So what we end up getting out at the end of this, so you can see I've got a list comprehension right here. I'm passing every sentence from my list of lists or my list of sentences into the position of speech tagger. So I'm tagging each individual token for my sentence in this list comprehension. And then I'm passing that to VStack, which we introduced all the way back last Monday. Or yeah, all the way back last Monday. Wow, how time flies. So that we can get everything into a NumPy array. What we get out is this new NumPy array that's 309 rows and 2 columns, where each row is a word, or each row is a token, and its associated part of speech. Okay. Does this make sense to everybody? Are people familiar? So this seems pretty hopefully straightforward and makes sense, right? Like, great. We actually have some really basic tools now that can actually break down sentences and actually meaningfully tell us, like, what parts of the English language they're stemming from. And you can do this with multiple languages. NLTK has this for, as far as I know, all of the European languages. I'm not sure beyond that. I know there are people working really hard on the Arabic languages. You'd have to look into other ones. I haven't done any work with that. This is going to start becoming really important because when we start wanting to talk about stemming words and lemmatizing words and cleaning up words, certain words are going to be best cleaned up by different algorithms. That's going to become really clear in just a minute. For anybody who's even vaguely familiar with text processing, one of the really important steps that you're going to know is that you're going to want to apply stop words. Stop words are the most frequent words in a language. It's things like is, and, they, but, this. It's words that are used almost in every sentence and because they're used so frequently, they almost have no informational content, right? Because you're not going to be able to tell the difference between a set of documents about dogs and a set of documents about cats by the word this, because this is going to start many sentences, right? This dog, this cat, this sheepdog. So there are lots of pre-built lists of stop words in Python that you can import and immediately use to filter out the most frequently used words of a language. Here, I'm going to actually use sklearn, so scikit-learn's the same package that we went over on Thursday. I'm going to go over theirs because I find theirs to be a little bit more complete. So you can see I'm going to import it. So from sklearn.featureextraction.text, import English stop words. I'm going to store it in a list. And I'm just printing out the first 20 here, but to show you, so we get a lot of things like hers, seems, do, now, something. These are just really generic words that are probably not going to have any informational content and certainly won't tell us anything about a scientific abstract, right? Won't help us be able to distinguish between a chemistry document or a biology document. Here the code's going to get a little bit more complex, but it's all going to be the same sorts of functions that I showed you guys last Monday when we were going through NumPy. What we're going to be doing in the cell is that we're going to be filtering out all of the most common words, all the stop words from the abstracts. So I'm doing a few things here. I'm creating a function real fast that'll automatically go through and just set to lowercase every single token that we've extracted so far, or every single individual word. That's because if you looked at the list of stop words, all of them are lowercase. And to filter out a stop word, basically all we're going to be doing is just saying, hey, is this word like research, or is this word like project, or is this word like chemistry? Does that word exist in our list of stop words? The problem is that programming languages are kind of dumb in that they distinguish between whether or not that first word is capitalized or not. So if chemistry in your stop list, or actually if is or they in your stop list is all lowercase, and they in your actual sentence starts with is capitalized, it's not going to be filtered out. So we're going to just want to set all of our words to be lowercase. We're using NumPy along axis to basically just make all of our words lowercase by applying lower to all of our tokens, just like I showed you before. And I'm using the NumPy in1D to find all of the cases where our tokens exist in our stop words. So let me show you what this actually looks like. So index should just be a Boolean array where wherever it's true, that's a token that exists in the stop words. So this is a pretty common word, and this was the first token that we looked at. It's telling us it's true. That makes sense. This should be in our stop words. This is a low informational content, high frequency word. So good, it works. So like I said, index is just this long Boolean array that tells us whether or not our tokens exist in the stop list. Does this make sense so far? Okay. So I should say this code is starting to get a little bit more complex, where I'm now in one line, I'm combining multiple NumPy functions in a way that I haven't been doing so far. So if you guys want, maybe on your time, really start maybe going through this and start pulling out the individual functions and seeing what they're actually doing. Because we have a Boolean array, the other thing that I should show you is that if you have a Boolean array, if you use the tilde operator, it'll invert every true to false and every false to true. So here, when I originally printed out IX, the first three were true, false, false. If I do tilde, we get false, true, true. The reason why I want to do that is because every time there's a true, it means that we have a high frequency word that we want to remove. So if I index into it and invert it, I get a false for every high frequency word, which means that if I index into our array, that means I'm going to be removing, not keeping. I'm going to be removing every high frequency word. So that's what's happening here. And you can see we went from originally having 309 words down to having 168 words. We were actually able to remove about half of the tokens. So about half of the tokens that we originally had in that abstract were high frequency, low information words. So we were able to remove them like that. And just as sort of an interesting note, after you do that, the main thing you should be noticing is that most of the remaining positions of speech are almost all nouns and verbs. We have a few adjectives in there, and a few adverbs, but that actually makes sense, right? Because things like determinants, things like conjunctives, things like prepositions, those are the most frequent English words, right? Those are going to be the words like the, and in, and of. Those are the words that are not helpful. They make it easy for us to comprehend language, but not to do analysis.
That tilde, does that work outside of this package, or is that?
Yep, that's
a normal function.
Yep,
in Python?
that's pure Python syntax. So it's super nice, actually. If you want to be more explicit, there's also numpy.inverse or invert, which will do the same exact thing. So originally, give you a quick example. Not the rain, it's not air conditioning. So you can see, so originally what we had is true, false, false, numpy invert, we just invert everything. But it's the same exact thing as the tilde operator, just shorter and prettier. Okay. here's where the positions of speech start to actually matter. So stemming and lemmatizing are two different functions, or two different processes that are frequently used when you're doing text processing to basically take words in their various what's the word that I'm looking for? In their various forms of the English language or whatever language you're in, and convert them down to their root word. So this takes dogs to dog, or it takes runs to run. And that's important because when you're doing analysis, run and runs are more or less the same word. You don't want to treat them as separate features. You don't want to treat them as separate tokens, right? Because it doesn't matter whether or not the dog is running or the dog runs. In either case, the dog is doing the same exact thing. So you want to convert that down to the base verb run so that when you're actually doing analysis, those phrases are actually being treated as the same feature. Does that make sense? That's a really, really core topic, and much ink and sweat and blood has been spilled over this in linguistics. But it's true. Don't look at me funny. The most interesting but intense people I've ever hung out with are linguists. Don't mess with a linguist, especially not a drunk linguist. So NLTK has a lot of different vectorizers and, lemmatizers and stemmers. These are based off of different algorithms that over the years different linguists have argued are the right way to doing stemming or lemmatizing. I'm going to show you a few of them here just to give you an idea. I'm not going to make you worry too much about this code. The most important thing to note is that I'm basically passing all these things into Vectorize. Well, first of all, I should let you know is that I'm importing all these things from nltk.stem. So these are all different algorithms used for stemming and lemmatizing. So there's the Lancaster stemmer, the Porter stemmer, the WordNet lemmatizer. These are all just different algorithms for converting words into their base units. You can read up on their histories if you'd like. What I'm basically doing is that I'm just passing our tokens through each of these algorithms just to give you guys a flavor of how they work on words. So it's just running. There it goes. OK. So up above in this table right here, it shows you a little bit of how each of these algorithms are actually working. So for example, our original token was fields. Its tag made sense. It was a noun. It was a plural noun. And you can see each of these algorithms has removed the s, has taken the noun from being plural to singular. So we went from field to fields. Here's where it starts getting weird. For example, we have the token bacteria. The Lancaster algorithm stripped out the IA from it, and we got to bacter, which is, I think, maybe it's Latin root, but don't quote me on that. But the other two kept it at bacteria. We have the word Greeks in here. The Lancaster and Porter stemmer took that down to just pure Greek and got rid of A, the fact that it was uppercased, and B, also got rid of the plural S. The verb detailed got taken from the Lancaster and Porter stemmer and got trimmed so that it was no longer past participle and was just put into its present tense as detail. You can see there's lots of different examples like this. The sort of general trend here is that different parts of speech are handled better by different algorithms. So in general, the WordNet is very, very conservative. It really tries not to trim too many things off. And you can see almost in general, WordNet almost always agrees with its original word. In fact, it agrees in over 80% of cases. Where it does typically do a good job is, for example, making plural nouns into singular nouns, which is helpful. The Lancaster and Porter stemmers are a little bit more aggressive. They're a little less conservative, and they are a little bit more, they'll really try to stem verbs specifically. So you can see resulting got trimmed down to result. Detailed, like I said before, got trimmed down into detail. And sometimes it's got some weird functions that we don't love. So for example, when we passed nouns to it, like for example polynomials, the Lancaster stemmed it to polynome, and the Porter stemmed it to polynomy. The sort of general trend here is that the Lancaster and Porter stemmers do a really, really good job with verbs and trimming them to their base verb and getting rid of like past participles or gerunds or whatever, going back to all that good stuff. And the WordNet's really good with nouns. The reason why this is helpful is because when we're actually going to be parsing these things, what we're going to be doing is I'm going to take all of the nouns, I'm going to pass it to WordNet. I'm going to take all the verbs, I'm going to pass it to the Lancaster and Porter algorithms. Therefore, the verbs are trimmed one way and the nouns are trimmed another way. And that way, for example, we don't make polynomial turn into something nonsensical. We still get polynomial out of it from polynomials rather than polynome. But things like detail gets trimmed down to its correct verb form. That's why that whole position of speech tagging thing can be really, really useful, is because when you differentiate among those things, you're more likely to trim it down to its appropriate root word. Does that make sense to everybody? So here's just some code below that's appropriately extracting out all the verbs, appropriately extracting out all the nouns, and then applying the Lancaster. Am I doing Lancaster or Porter? I think I'm doing Porter, and I'm doing the WordNet tokenizers respectively for the verbs and the nouns. Does that make sense to everybody? Great, okay. So just know you have options. You don't have to just stick with one thing, and you can use multiple algorithms and use position of speech in order to sort of improve the interpretability. The other thing I should say is that a lot of people do this, they don't care whether or not your corpus at the end of text processing is human readable, as long as it just gets everything down into the same root verb. So they don't care if polynomial becomes inscrutable and becomes polynome, and you really don't fully know where that came from. This really has to do with basically what ultimate goal your text processing is for. And if you have a smaller corpus, it might be better to try to bring everything down into its constituent roots and be very, very liberal in your removal of stems, or in your trying to reduce down to stems. If you have a really large corpus, like in this case where you have 10 years worth of abstracts, you can probably afford to have things like run and runs or running and run be separate things, because you'll get enough of those that it'll still aggregate in the end. The other thing I want to show that I guess apparently won't work for half of you, though we'll get that fixed, is that Python also has spell checking. So it's kind of rare nowadays to do spell checking on corpora, but if you wanted to, it's an option. The enchant library is one way to do this. So for example, I just imported enchant. I've initialized a new enchant object, basically saying that I want to do spell checking on the English language. So for example, the spell check object can do the .check attribute to basically look and see whether or not a word is spelled correctly. So I can check to see whether or not hello with one L is spelled correctly, or whether or not hello with two L's is spelled correctly. So here I get hello with two L's is true, meaning that it is spelled correctly, and with one L is false, so it's not spelled correctly. Apologies if this is not working for people. I will find a fix for this. The other thing that you can do is use the suggest attribute, where it'll actually print out a bunch. If it's not spelled correctly, it'll print out a bunch of suggested alternate spellings. So you can see the third one here is the actual thing that we're going for, hello, but you can also get Helon and help and Helios and all those great things. We could do this, for example, we can basically embed a list comprehension here that basically says, find me all the words that are not identified as being spelled correctly in our abstract. Which here actually is kind of interesting, because basically almost everything we're getting is just proper nouns like Archimedean or Berkovich or Calabi-Yau. And you can see sometimes, especially when you're doing spell checking, the suggestions are pretty accurate. So the first suggestion for Archimedean is Archimedes, which is its proper root. But for the lesser known Calabi, I'm so sorry, Professor Calabi, it recommends calabash, and he's most certainly not a fruit, so doesn't always work. So a lot of people don't use spell checking. It is an option you guys have. The other thing that I should say is that if you want a really good intuition for how to actually build spell checking, there's an amazing tutorial for this. You can build with just this much code, you can have an entire word-based, or like a word similarly accurate to Microsoft Word spell checker with just these lines of code and a large enough corpus. It's really, really impressive, the just internal logic that spell checkers are built off of. A lot of it just has to do with comparing the similarity of strings. So basically, like, how likely is it that something that is 5 characters long matches a similar string that's just 6 characters long, and just the right algorithms by which to search across those. If you want a really cool tutorial on this, I really recommend go through this. I had never done any of this, and it's too much to go through here, but it's really cool just to see really smart people thinking through cool algorithms. Okay. So to recap, we went through encoding. We went through tokenizing from sentences down to words. We talked about positions of speech. We talked about stemming and lemmatizing. We talked about stop words. And we talked a little bit about spell checking. That is 90% of most people's text processing, pre-processing scripts. That is, especially if you have a large corpus or a large amount of text, that is basically 90% of what people do. You can get really, really far with knowing that little amount of code if you want to do text processing. If you're interested in higher order linguistic problems, probably need a little bit more than that. But if you are interested in just basic things like sentiment analysis or topic modeling, or just predicting, actually as we get through some examples, if you actually just want to be able to predict whether or not a document is a chemistry document or a biology document or a humanities document, that's all you need to know. Because in fact, based off of all of the code that I defined above, I just put it all into one for loop that is written out in more code than really needs to be, but just for readability. This is all the code that I wrote. It's all the code that we defined above to process all 100,000 abstracts that we had downloaded. It's about 50 lines of code, and it doesn't need to be 50 lines of code. It's just for readability if you guys want to go through it. We could go through it again, but it literally is just all the code that we just defined above. This took about, with 10 minutes, to get through 100,000 documents. It's remarkably fast. That's the other beautiful thing about NLTK, is that it's a very, very fast library. Just be aware that doing different linguistic operations require different amounts of computational time. Spell checking is slow, which is another reason why people don't like doing it. Stemming is fast. Lemmatizing is slower. Stop words is incredibly fast. So the other thing you should know is that depending on whether or not you want your algorithms to be running in real time, if you want to have like a real, like a Reddit bot or a Twitter bot that can do text processing in real time, maybe you want to leave out a number of these features. But if you really want to clean up your corpus and have a really, really solid body of tokens, and you only need to go through it once, there's a ton of functionality, and you can just go grab a coffee and let it run for 10 hours, and you'll be good. Okay. Questions? Okay. We have the option, it's 8. I'm going to go through a few examples of some machine learning stuff that we didn't talk about on Thursday. So we're going to do a brief tutorial on naive Bayes classifiers, and a brief tutorial on topic modeling as applied to this abstract data, just to show you some of the power of NLTK plus scikit-learn. It's 8. Do people want a 5-minute break, or do you want to just charge through all the machine learning stuff?
Let's take a break.
Yeah. 5-minute break.
What are you trying to do over here?
Just tune that leaflet down. Maybe I'm running for it. And it's
Oh, nice.
the HTML kind of rendering on our side. So I've got it to work because I uploaded it to Drive. I think it's something with emailing over Gmail. Because I sent it to other people today and they could open it. But like, the
You
people.
sent it to Mallory, like,
No, it worked because I uploaded it on Drive and she
Oh, right.
and then I was going to publish it to the web. So much text analysis here.
my whole project that works on it now.
Really?
I was working today with this company called Ravenpack that like sell data, and they've done some ridiculous stuff. They process like hundreds of thousands of news articles per day, and they each article they categorize different events being discussed in the article, give each one a sentence score, and then rank the importance of the events. And they're like, yeah, just ridiculous. There's a data science guy from Spain who worked there, like going through it all.
So what are you guys doing for them?
One of the other teams is considering like buying the data to use, so they called a meeting. My team is just like gonna be just like more simple things, but the actual processing is like complex. So like we're just using like have internal memories, for example, and they want to like see if internal memories have any predictive power or like
How people are performing or something.
yeah, exactly. But I have to do like paragraph wide sentiment, so like dependency within the sentences and like that kind of stuff.
So it's not like
Can't be-
how complicated is your sentiment algorithm? Is it just like positive, negative words, or is it like
It's my job to make it. I have like 6 months.
oh, so you can make a fancier one then?
Yeah,
Pretty
so I've got
positive
like
words.
I'll read this whole book.
Yeah.
I read the first class from Columbia. I'll probably read every single slide from that. It's all online. And I'll read this whole book.
This is such a huge deal.
Yeah, I'll become like an expert on this shit.
Yeah. Take it 6 months.
Yeah.
Books are free. It's good.
Yeah.
Nice and long, I'm sure.
It's quite quiet at once when you sit there and read it.
Pretty good deal.
Yeah.
None of the stuff we went over in class was like super, super complicated.
Just
But
like-
I'm sure this stuff.
Yeah, there's like little things that like, I wouldn't think to do.
Like, how do you do sentence by sentence? Sentiment.
We haven't done that.
You're gonna learn it?
We've only done the bag of words thing.
Just like the most basic thing ever.
Yeah, take a whole bag of
Are they
words.
trying to teach you?
No.
Ah.
One guy went to like, he has a comp sci undergrad, and he knows a lot about it, but he's like, it's your project.
You fucking do it.
Pretty much.
Funny.
Yeah. Everyone's working on their own different things. So,
Oh,
mine's like the most data sciencey.
yeah.
I downloaded Anaconda at work, but
You what? You download Anaconda?
yeah.
See, they let you like download things.
I found a way
Can you
of
bring
getting
your own
it.
computer in?
You can, but you can't use it. Because like the data is proprietary. How's your research thing going?
Fine. As long as you can open the shit up somewhere. It comes in handy. People are very impressed by it.
It's cool.
Yeah. We built like so I have to say, this is the client is this Jewish organization like the UJFA, which is the biggest like Jewish community building nonprofit in the US, and we're thinking about building a community center in like Park Slope,
Nice.
Brownstone, Brooklyn. So we're like scraping for like all the Jewish community centers and different like groups that
Okay.
meet in Brooklyn, and then like providing them a landscape of like what's going on right now. So it's like a pretty basic map, but these are like all the Jewish community centers.
Hi.
And then these are which are like individual meeting spaces. So I like layered it.
So I guess what people like get to play around with it.
Yeah. So this is just kind of give them a lay of the land. This is like our first presentation to them. And it's to kind of like,
Well, that's
this
weird.
is
So you're
what's
getting
going on.
permissions
Like, how
issued.
much more
Yeah.
detail do you want
Is
on
this is your account, right?
It's pretty complicated because like you don't want to come and introduce
Well, that's
the
bizarre.
community
Why
space
would it
when they're
not be-
already small individual groups
I mean,
meeting
it's
everywhere who
Yeah.
rely on renting out their space. You don't want to fuck
'Cause
them
that's-
over
that's-
by
that's sort of the
using your
beginning of
space
the
in.
Yeah.
problem
So
here,
you
so
kind of
it's
have to
saying
get a
that-
really good lay of the land before you decide where to put it, and then you also
Yeah.
reach the maximum number of people.
How did you get the addresses?
Just go online, you like Google Map it.
Really?
Yeah.
Okay, can we
Pretty
troubleshoot
sure
this at
latitude
the
and
end?
longitude.
Is that okay?
I'm sure
I
there's an
think
easier.
there's a few things we can
I'm
try,
sure there's
but
an
that's
easier way
stupid
to do
to
it.
do.
Like at
That's
some
super
point, I'm gonna
stupid.
have
Because as
a
long as
list
you're
of
on
like
account
500
and you
places,
install
I'm not
them
going to
on
Google
your
Map every single one.
Yeah.
But it's also difficult because when you search
We'll
things on
think
Google
about this.
Maps, like the
That's
first
super
thing
weird
that
that
comes up is
comes
always the thing. You have to
Yeah,
go find
sure,
it
sure.
before you
Yeah,
go on it
yeah.
and get
Thank
the
you.
land.
Yeah.
But I'd like to figure out how to do that.
It's super bizarre.
What's Mike doing?
Nothing now. I had
Is he
drinks
around?
with him the other night. Yeah. He got back and he's just hanging out for the next couple of weeks. But we should all. He's leaving July 1st, so we should all go get a beer before that.
Yeah. Pretty soon, isn't it?
Yeah.
Yeah, shit, it's like
Next week.
next week.
Yeah. I'll talk to him. We're going out to dinner with him and his girlfriend on Thursday.
Nice.
So I'll talk to him then.
After the class.
Yeah, I'm not going to class.
Yeah. Also, I mentioned to Chelsea about your GBA thing. Are they
Oh,
actually
yeah.
hiring or not?
They're hiring, but they're only hiring bilingual people right now.
She does speak Spanish.
That's true.
Is it worth it or not really?
The job?
Yeah.
I don't know. If she wants to like meet Amelia, I'm sure she'd be happy to tell her about it. She likes her job some days and doesn't like it other days.
Yeah.
It's like she likes what she does and likes interacting with people, but it's also a bureaucracy and it's a little soul crushing sometimes because they're super unionized and Amelia likes to like work after 6:30 so that she can finish her stuff. But they like throw her out of the office at 6:30 and like.
That sounds good.
Yeah.
But
Like if you're looking for work-life balance, it's great. You used to like apply to like stay late to get overtime for every
Oh, really?
day you stay over. Yeah.
Would she be keen to go for like coffee or something to chat about it?
Yeah, for sure.
Can I give her a number or something?
Yeah. I'll give you a number.
Because
You also get a lot of So if you work extra hours, you get the overtime. You can take it as time, so you can get extra vacation.
that's pretty cool. So what's the actual thing? It's the New York State.
No, it's the public engagement unit of the city.
I forget. I'm sure in message to like tomorrow sometime, so you can like tell her. You can give her a heads up. Like,
Yeah, yeah.
tomorrow. But she's free all day, so may as well like give you an opportunity.
Yeah.
She's signing up for these volunteer organisations right now.
Is she like taking some time now to
Starting
figure
to
out
enjoy
her
it.
shit? Yeah.
Like last week was kind of stressed that grandma died.
Yeah,
So
that's
that was a fun thing. I just texted
I'm still Jack Cumas on my phone.
Glad there's only one.
Yeah.
Exactly, right?
Nice. Cheers. Media will probably just piss at you. She has to go to coffee. I'm already doing my extra work. She can't say past 6:30, so she can't take any time out. She starts at 10:30, right?
Yeah, 10:30 to 6:30, and you get an hour for lunch and an hour. So usually you go out into the field in the morning.
Yeah.
And they give you an hour for lunch and an hour to travel back to the office. It's 2 hours off in the middle.
And how bilingual do you be, like writing an essay in Spanish or just chat?
Probably chat.
Yeah, because she's somewhere in between. Like, she can't like write.
I don't know. Like I don't know if they take someone without any organizing experience. Like,
Yeah.
I know that they definitely lower the standards.
All right,
for
well.
people with,
Okay. Well, it's worth it anyway.
yeah, pretty much.
A few of you guys get to while we're waiting for a few more people to trickle back in. One thing I wanted to show you guys earlier last week, but got cut out for time. One reason why the Jupyter Notebooks are really, really nice is you can do interactive plotting, which can be really helpful, for example, if you want to. Something I frequently find myself doing is needing to better build an intuition for understanding from probability distributions. So by pulling out from scipy.stats some probability distribution I haven't worked with before, and then by tweaking different parameters of that distribution, just generating random data just to get an understanding of how setting, for example, different priors might be influencing my analysis, at least in a Bayesian context. One way to do that, you can import this really nifty library, which is IPyWidgets, and specifically the interact function, which will allow you to create these little slider things, which allow you to sort of very quickly drag sliders around and define different parameters that you'd want to use for plotting something. This was supposed to be Megan's brain, but we can't get that working, so it's my brain instead. But for example, so what I've done is define a very quick little function here, plot, which all it does is just open up a new plot, take some brain data of myself that I loaded, and just plot going along sequential slices on the z-axis. And you can pass that to this new interact function. You can give it the function you wanted to iteratively plot over, and you can tell it the start and end points on the slider. And you can just slide this now and do interactive plotting. And in this case, you can slice through the, what is this, the axial slices of my brain? I can't remember. No, axial's down. It's not coronal, it's sagittal. That's what it is. And you can see everything. I'm still like just, I can show you the hole in my brain. Somewhere in my parietal cortex. Is everybody back? Are you all? Otherwise, we're just going to do a great neuroanatomy session.
Yeah, they're all back.
Great. That's my brain. But it's really easy to do this, for example. So just to give you a better idea.
What's this? This is the code thing.
Yeah, it's weird.
You made the map of Java connected it off.
This doesn't matter. Okay. Point is, if you want to do interactive plotting in the notebooks, it can be really, really helpful. I do this very frequently when I'm trying to understand like how different tweaking parameters on a model actually impacts my data, or how it impacts like usually a Bayesian model, but you could do it, for example, to just show you how tweaking different features of a pre-processing script censors out various data points or whatnot. So, and that way it just makes it really easy to build intuitions. Okay, in the interest of leaving some time at the end for questions, we're just going to blow right through this. I want to show you guys very quickly. So that script that we went through up above went and produced this folder called tokenized, which just has many, many, many text files. So if you downloaded this from the Dropbox, that's what's here. If you open any single one of these text files, what it is just the abstract after it's been tokenized. So you can see none of this is really interpretable English. It's just the cleaned up, stop word filtered, stemmed words from each individual abstract that we would have. And this is like some abstract from 2006. Let's actually do some analysis on this. So to remind you all, again, this is many, many, many abstracts from the National Science Foundation. That means all of these abstracts have some sort of important information that has to do with different scientific research and things pertaining to science. How are we going to analyze it? Well, the first thing that we need to do is we need to be able to basically just tabulate how often are we seeing each individual token. So how often do we see the word research? How often do we see the word chemistry? So on and so forth. To give you a really, really simple example before we jump into the complicated example, let's say that we have a really, really basic corpus. And when I say corpus, I mean just a body of words. In this case, we're going to have 20 total words. We're going to have the words A, 1, 2, 3, 4, 5, 6, all the way through 10. And we're going to have words B, 1 through 10, right? Like a weird convoluted game of Battleship. And the other thing I'm going to do here is I'm going to generate a bunch of those words, and I'm going to store them into documents where there's going to be a transition probability, where for every time one of my documents starts with an A word, it's going to be 10 times more likely to transition into another A word. And every time I start with a B word, it's going to be 10 times likely to transition to another B word. That's what this lovely little matrix shows here, is that if you start in A, you're likely to stay in A. And if you start in B, you're likely to stay in B, but you're not guaranteed. So we're going to simulate a bunch of documents as such. And here's 3 example documents. You can see I started with A1. And for most of it, in fact all of it, I stayed in the A's. Here, I started with an A, and towards the end I transitioned to the B's, just by chance. Here I started with an A, and very quickly I transitioned to B's. The point I'm going to try to get across here is that even with this totally nonsensical language, I can count up the number of times each of these tokens appears across the documents that we've just randomly simulated. And just based off of that very small statistical structure, the fact that A words are more likely to transition into further A words, and B words are more likely to further transition to B words, you can fit all sorts of models. The way that we're going to do that, first of all, is we're going to import from sklearn, the module that we handled last week, this count vectorizer function. What this is going to do is we're going to pass into it a list of lists, that's documents. So actually, just like last week, I'm going to say this just to fully ram this home. We're going to initialize the new count vectorizer class, and then we're going to use the fit attribute just like we did last week when we were doing support vector machines. And what that's going to give us is this new fit that has all of the same tokens that comprised our corpus. So you can see it's all the A words, A1 through 10, all the B words, B1 through 10. And I'm going to transform that across our documents so that we get 100 documents by 20 words, because again, there's 10 A words, 10 B words, and I made 100 documents. And this matrix looks a little something like this. This is just the frequency at which different words are showing up across the documents. The documents are on the Y, our words are along the X, where it's brighter, that means it appeared more times for a given document or not. There's a little bit of, it's hard to see in here, but there's actually weird implicit statistical structure. How do I know that? Because we're going to take the logistic regression support vector machine that we didn't cover but is present in sklearn. And based off of those models, we're just going to basically train it up on the documents or on this sort of sparse frequency count matrix that we get at a count vectorizer. And we're basically going to ask what features or what tokens, which A words and which B words, predict whether or not the document started with an A word and or whether or not started with a B word. And you can see, ideally, this would be the ideal case in the sense that if basically, in general, what we're finding here is that there are negative coefficients on all the A features, meaning that the A features predict documents that start with A, and the B features predict documents that start with B, which makes sense because of just that small statistical, man, this example. Basically, it's just because this small statistical structure where there's just an implicit statistical structure where B words are more likely to follow B words and A words are more likely to follow A words, meaning that just that totally nonsensical statistical structure that we inserted to make up a totally nonsensical language and a totally random set of documents, we can actually extrapolate and fit models with 80% accuracy where we can predict whether or not those documents belong to the A words or belong to the B words. That was a pretty convoluted example. Did that make sense to everybody? Or was that like, stick to the actual stuff? Cool. Thanks, guys. I appreciate your support. So that's a very simple case with 100 documents and just 20 words. We are now going to fit this to 100,000 documents and a lot of different scientific words. But everything's the same exact case. We're going to import the count vectorizer, and again, what that's going to do is return to us a sparse matrix that basically says, for every document, did or did not this token appear? So in document 1, did the word chemistry appear? If so, make it 1. If it appeared twice, put it in the cell that it appeared twice. If it appeared 3 times, make it 3, so on and so forth. And we're going to do that for every single document and for every single word that appeared across our entire corpus. So we're going to initialize it, just like we've initialized all the sklearn objects. We're going to now pass a list of documents, which was that huge file of documents that I just showed you guys from before. Again, it's everything that lives inside here. I'm just basically passing in one giant list that has the file paths to all of these. And that's it. I'm just letting it fit. And what it's going to then do for us is count up the number of times all of the unique tokens appear in all of the documents. And that's what it's doing right here. And we get out CMAT, which is just our count matrix, which is just going to be a sparse matrix, meaning that wherever there's zeros, it's technically going to be encoded in a sparse format in NumPy so that it actually doesn't eat up as much memory. So that the array doesn't actually eat up as much space in the cache. Pre-computing this is good. This takes about 5 minutes. It's actually not pretty fast on the whole. But what I've done here is I ran these operations and I just saved out the outputs to that so that we didn't have to rerun it in class. I'm just reading it in using NumPy. It goes much faster when I read it in. And what we get is a sparse matrix that is 134,000 documents by 146,000 unique words. And we can actually take a look what that looks like. So for example, we can quickly count. What we have here on the X is the rank of the word, where we're ranking it by how often it appears across the entire corpus. This is in scientific notation because certain words appear a lot, or the fact that we actually have tons of words. So like I said before, we have about 100,000 words, so it goes out 10 to the 5. What you can see is that we have certain words. The most common word, the first word, appears got 300,000 times across our entire document. And the second most common word appears also similarly. The 10th most common word appears around 100,000 times. The 100th most common word appears closer to about 10,000 times, and it goes down. This is a classic power law distribution, which you're going to see a lot of when you're working with text data. Basically, the most common words appear orders of magnitude more times than the least common words. We can also compute the feature ratio, which basically asks how many times does this word appear across the entire document? Because just because a word appears many, many times doesn't necessarily mean that it's appearing a lot across every document. It could appear 10,000 times just in one document. But we were seeing that, for example, the first most popular word appears in about 3/4 of the documents. That's important because words that are appearing across 3/4 of the documents when you have 100,000 documents have very low informational content, right? Like, you're not going to be able to discriminate much with those words because they appear in everything. They're not going to be helpful for training machine learning models. If you guys like word clouds, there is a word cloud package in Python where basically all we're doing here is we're taking out each individual feature from our matrix and the number of times it appeared, and we're just feeding it into this word cloud function as a dictionary of just the feature or the token and the number of times it appeared, and it'll automatically compute these lovely little word clouds for you. Apparently that's a divisive visualization.
Just to me, everyone else seems to be.
Okay, we're going to let this one go. Basically, one important thing here is a different director. We're going to skip over that part. That's not important. Go through the actual document if you really care about that. There's some other things we compute about our tokens here. So for example, we can look at how many times in general. Let's look at in the tails of our distribution. How many times do our individual tokens appear? How often can we count, for example, singletons, which are tokens that only appear once? Turns out that of our approximately 160,000 unique tokens, about 70,000 of them only appear once. That's incredibly, incredibly common. Most of the words in linguistic corpora are going to be words that only appear once across thousands of documents, especially in web stuff, because most of those are going to be typos that you won't be able to correct, or weird encoding formats issues where like you get a string of 100 A's all in a row. Or in the case of scientific data, you'll get random molecules that only appear once because only one person is investigating that molecule. Or in Twitter data, you'll get maybe that weird hashtag that only appeared once and never caught on. And you can see, it's actually pretty remarkable. In terms of words that are appearing 10 or more times, that actually constitutes a pretty low amount of our corpus. It's only around 40,000. So that's about 1/4 of our corpus actually appears 10 or more times. So most words appear very low frequency. There's some code here that's all about how to remove low frequency words. So here we're just going to remove singletons, so words that only appear once. That's useful because otherwise if you're trying to fit a machine learning model based off of singletons, you're going to have a lot of just columns in your design matrix that are only going to be necessary for one thing, and that creates a lot of unnecessary degrees of freedom, so we're just going to remove all those. The other thing that I'm going to do is I'm going to write a line of code right now that's going to remove the most frequent terms. So anything that appears in more than 20% of the documents, I'm going to remove. That's an arbitrary threshold. You could do it for lesser. Pretty often people will take documents, especially if you have, like, in this case, like 150,000 documents or 130,000 documents, maybe a 10% threshold is fine. Because again, you want to only include words in your corpus that are going to have discriminative value, that are going to allow you to discriminate between different topics in your data. Something that appears in 70% of the documents has no discriminative value. I'm just going to replot it after we do that. You can see we get words that appear far fewer times. Before, we got words that were appearing like 300,000 times. Now we only get that 40,000 times. And you can also see that the feature ratio is, as should be, much lower now. Now it's, the starting point is 0.2 and very rapidly drops off. The most common machine learning model that is often fit to this sort of data are naive Bayes classifiers, just because they are incredibly simple models that basically just look and see. When you're training up a document, it basically just asks how often is this word associated with a given document. So it just basically counts things up. So How often does the word dog appear in the dog documents? Hopefully a fair amount. We're just fitting this here, and again, we're just running the same sort of code that we introduced on Thursday. So naive Bayes classifiers have again, a sort of sparsity prior where you can force things to be more homogeneous, which sort of reduces the influence of infrequently appearing and highly frequently appearing tokens, sort of helps evening it out. So we're just going to do cross-validation to find what level of sparsity we should be inducing. We're doing tenfold cross-validation. And you can see, actually, in this case, the default parameter of 1 does really well. When you set it higher, you get worse and worse performance, which is good, which makes sense here because we actually cut out a lot of the non-helpful words. So we actually want to let the helpful words do their job. And in this case, we're just doing a further example as we covered on Thursday, where we're just going to fit, again, a multinomial naive Bayes classifier that we imported from sklearn up above, using the same syntax that we introduced on Thursday. Just going to fit it to our data. And we're just going to try to predict which directorate did this come from. Now, at the National Science Foundation, there are 8 main directorates that are basically split up by their respective scientific topics. So there's a directorate for engineering, and a directorate for information technology, and a directorate for education, and a directorate for naval explorations, which is lovely. When we fit the Bayes classifier, what we basically get is a feature count, which basically just, as we talked about before, just basically counts up how often did a given feature, or in this case token, appear for a given document. And it's going to basically train on that to try to predict what set of documents came from which directory. And you can see we're actually getting really high accuracy. We're getting nearly 80% accuracy. So on the training data set, we got about 79. On the test data, we got about 78. And what we're going to do is we are going to find what are the most representative features, or in this case, what are the most representative tokens for each directorate. So, and this is after fitting it to our data with a multinomial naive Bayes classifier. So for the directorate for biological sciences, the most representative features are words like plant and species, meaning species, cell, gene, protein, so on and so forth, things that you'd expect to come up in biology. For computer and information sciences, you get things like software and algorithm and computer. For education, you get things like learning, faculty, school, course, institution, college. So, and I can give more and more examples. The really, really important thing to take away from this is, remember, so everything I showed you up above in terms of the pre-processing was really, really straightforward. We didn't do anything too fancy. The steps that we did, we read in all the data. We applied stop words to get rid of the most frequent terms. We stemmed some words. I didn't even run any spell checking in the examples up above, actually. Really, really straightforward pre-processing. And then in terms of fitting these models, the only additional sort of post-processing steps that we did is we removed all the singletons, and we removed the words that occurred in more than 20% of the documents. And from there, we were able to get 80% accuracy in actually predicting what institution this grant was awarded from, which is remarkably good. Which is the really nice thing, is that text data, when you have a large enough corpus, is super forgiving if you have lots of weird words in there and lots of weird misspellings, because in general, if you have a large enough corpus, law of large numbers, you will get enough informational content, the cream will begin to float to the top, really. So just sort of fine-tune the amount of work you want to put into your pre-processing, probably based off of A, the goals of the analysis, but also B, based off of the amount of data that you actually have available. If you've got 10 or 40 years worth of grant data, you've got a ton of data. If you can spend a month just mining Twitter and get 2 million tweets, you probably have plenty of stuff and you don't need to worry too much about the pre-processing. You're probably going to do an okay job, even with frequent misspellings. The other really important thing I want to show is just rescaling text data. So the way that we scaled everything here was just pure counts, right? So we basically just looked up and saw, for the biological data, what words appeared most often, like genes and species and plants and so on and so forth. Another way to scale your data is known as the term frequency inverse document frequency scaling. What this does is basically puts sort of a weighted sample on your count data that basically says, make the most, basically weight the data by the tokens that are the most frequent for a given document, but not across the entire corpus. Meaning that if a word is very, very frequent, but appears across 70% of your documents, weight that word really lowly in terms of its importance, because it, again, has very little discriminative content. And weight the words that appear kind of frequently, maybe middling level frequency, but only appear in a select number of documents. Weight those really highly, because those probably have very good discriminative value. It's really easy to do that with sklearn. So just as we imported the count vectorizer before, we're going to take the TF-IDF transformer. What it takes in is just the count matrix that we previously computed from the count vectorizer. So you can actually just feed the output from the count vectorizer step straight into the TF-IDF transformer step and immediately compute a TF-IDF matrix. I'm just going to basically show you, instead of getting pure counts, which are obviously going to all be integers, now you get these weird ratios, which are their relative importances, right? So downweighting words that appear frequently across all the documents, but upweighting words that appear frequently in selected documents. We're just going to refit all the models. What you can see is that, in this case, we already had pretty good performance, but you get a slight increase in performance if you do TF-IDF, because again, you're downweighting words that appear frequently across all documents and really just upweighting words that are selectively useful. And we're just fitting the same thing as before. You can see we get a slight improvement in performance by like 1%. And it doesn't really change the words that you get out here. Finally, one other nice model that's built in is the topic modeling. So anybody who's done text mining or text analysis before is probably familiar with topic modeling. Please raise your hand if you're familiar with topic modeling. Okay, I'm going to give a 20-second intro to topic modeling for the few of you who haven't seen it before. The most common topic model is the latent Dirichlet allocation model. It's a really interesting, nice model that basically says, if you have a document, documents tend to be about topics. So if I have a document that's about dogs, the topic of that document is dogs, and maybe it's also about outdoors or walking or kibbles and bits, other topics that are frequently associated with dogs. And every topic is going to be made up of a distribution over words. The dog topic is going to have a high probability of being associated with things like dog and wagging and tail and walking and kibbles and bits. Meaning that if I saw a random document that is highly associated with the dog topic, I should see all of those words in that topic, but I shouldn't see words associated with cats in that topic. What we have when we're fitting this model is we have a bunch of documents and we have a bunch of words, and we're just trying to infer the latent variable that is the topic based off of the number of times we're seeing certain words appearing in documents, basically essentially just off of all that count data. Please nitpick me if that was a bad description of topic models. The main point I want to get across is that topic models can be super finicky to fit, but scikit-learn, sklearn has a pre-built topic model ready to go. It's pretty robust. You could tweak it to your heart's content, but the default straight out of the package parameters are actually pretty good. It's a little slow. For all of this data, it took about 7 hours, which is super fast as compared to like MCMC sampling time, but maybe slower than certain other packages that would do it directly out of C. But we can fit topic models. Basically, in this case, just to show you an example, I'm taking the same sort of count data that we did before. I'm finding 100 topics from it, and I just want to show you some of the things that it finds. So for example, it finds a topic that seems to be about computers, because it finds code and error and storage and binary and disk, and it finds a topic about what appears to be multidimensional math, because we have surface and dimensional and deformation and depth, and there are some other cool ones in here, like you got a social policy topic and things like that. This took about 6 hours to fit, but it comes for free. You can tweak it. And you can do other really nice things with it, just with the code that we talked about on Thursday. So here I'm fitting a PCA and then a k-means to the outputs of the topic model to try to cluster the topics. That might be a little bit hard to see. This red cluster up here seems to be clusters about like chemistry and measurements. There's a cluster out here that has a lot to do about sort of biology and biofuel. This sort of stuff out here seems to be more of a technology based. It's got words like algorithm, software, interaction, computational that come for free. The other cool thing that you could do if you were interested, for example, is look and see what topics were most predictive of NSF funding. So for example, we can find, and you can do a weighted average, so weighted across topics, what topics typically are highest funded. Turns out that things like very basic things like instrumentation are very highly funded by the NSF, so building the Large Hadron Collider. Also nicely, the education topic seems to be highly funded, which is good. And so you can do interesting things like this, just to give you an example of some interesting things you could potentially do through topic modeling. The main thing I want you guys to take away from there is just like there's tons of nice text processing machine learning models through sklearn that are optimized to read in text files that are all spit up by NLTK in one-click pipeline. Again, everything in this document, if I were to write to be as concise as possible rather than as readable as possible, would maybe be like 70, 100 lines of code. And that would be for writing an entire text preprocessing pipeline, all the way through doing classification with multinomial Bayes, naive Bayes classifiers, and even doing topic modeling and things like that. And all probably about 100 lines of code. So the big high-level takeaways from this is Python is very fast. It's really easy to work with text. I showed you NLTK. There are a lot of new specialty packages that are coming out now, like Spacey and Scrapey, and we'll talk a little about Scrapey tomorrow, that are designed to do rapid web scraping and feed that directly into these large, beautiful pipelines for doing rapid text processing that are meant to scale. So in this case, maybe this code doesn't scale. This is 100,000 documents. If you did it on 10 million documents, it would probably take a few days to run rather than a few hours, which is remarkably better than when I first started doing this. But anyways, things like Scrapey and Spacey now, for example, promise to deliver these things, especially because you can push it to cloud processing in hours as opposed to days now. So this is just to sort of get your feet wet with text processing in Python, but know that there are really, really powerful high-end packages just beginning to come out because there's huge, huge demand to be able to rapidly mine Twitter and Facebook and then immediately push to Amazon Web Services and be able to do really fast, within a day, crazy amounts of text processing for all of your social data needs or economic data needs. So with that, that's a really high-level overview. Most of you, it sounded like, did some text mining stuff before. If this was your first time seeing it, I'm sorry that this was a very brief overview. Definitely check out the NLTK textbook. It's free, it's online, it's super thorough. It goes through a ton of really interesting examples. And also check out some of the other links that were in the PowerPoint, like Ken stuff. It's really, really cool. It gives you a lot of really cool code base in Python to do some really cool immediate examples for political data and social data and economic data. That's it. Oh, and as always, there's also exercises and solutions. So what I should say is for the exercise, if you want to do it, you would have to download it. It's in the email that we sent out earlier. It's, I think, about 100,000 user reviews of food products from Amazon. And it's just a very simple sentiment analysis set of exercises where you can very quickly go through and try to figure out what are positive reviews and what are negative reviews and what are the tokens that are most representative of positive and negative reviews. Spoiler, I'm incredibly disappointed is probably a negative review.